So welcome. I'm speaking twice today. Perhaps the organizers thought that my talks were the most basic and elementary, and I hope you think so too. I'm going to start off with an introduction to explain the goal of my talks and also the goals of what I hope the students will work on now and in the future, and for many of you too. So the basic object that we shall consider will be a modular form. So we usually think of modular forms as given by some Q expansion. Let's suppose we start from n equals 1 to infinity, and let's just imagine that our coefficients are in Z. So here f is a modular form. So what we might be interested in is in congruence properties of these integers a n. So there's one situation in which we have quite a lot of information, which is namely suppose that actually f is actually a Hecker eigenform. So this is a favorable situation, and one of the reasons why it's favorable is that associated to f, there are lots of interesting arithmetic objects we can associate it to it, and in particular we can associate to it a Galois representation. So if we choose, for example, a prime p, then associated to f is a representation of the Galois group of Q, so in this case, GL2 of ZP, such that the trace of the Frobenius element at L is equal to AL for all but finally many L. So for all L not dividing maybe some integer and some prime. So this was used to great effect by Serre and Swinnerton and Dyer to explain a bunch of classical congruences, for example, some particular modular forms, for example, the Ramanujan delta function. But this is not somehow what I'm going to be talking about. This is perhaps related to what Toby will talk about. But so let's in fact instead not assume we have an eigenform, but let's just consider we have a general case. So now let's just suppose we have an f that is now a modular form, but no longer a cusp form. Or no longer an eigenform. So if it's a modular form, one thing, a basic important fact about modular forms is that it will belong to some space. Let's just give it a name, it's not so important. It belongs to some space that's finite dimensional. And moreover, this finite dimensional space, not only does it have eigenforms living inside it, it can actually be decomposed into a sum of eigenforms. So this is not a somehow trivial consequence of finite dimensionality. It requires, in fact, an extra property, namely the existence of some nice inner product, the Peterson inner product. So in particular, the existence of the Peterson inner product. I hope this is how you spell Peterson. Inner product. The existence of this Peterson inner product implies that given a form, you can decompose it as a finite sum of eigenforms. And explicitly, in terms of this Peterson inner product, let's write it like this. You simply pair it with the eigenform, and then you normalize the eigenform. So you have this times phi. So here these phi i's are now eigenforms. Oh, yes, I'm off the bottom. So I'll just say it, these phi i's are eigenforms. And I should say, so let's just even assume we start with our f, which has coefficients over z. Then when we write this as, say, a sum, I mean, these elements here are, well, a priori they're complex numbers, but it turns out that they're actually algebraic numbers. Not necessarily integers, but they're algebraic numbers. And because of the existence of this decomposition, well, by the first part, you can understand congruences for these eigenforms using Galois representations. And then you understand congruence for these eigenforms, and then you have a sum with algebraic coefficients. So you understand congruences for f by understanding congruence for these eigenforms. So that's a basic way of understanding, for example, congruences for modular forms. Okay. So this is somehow a story that is well known. Yes, thank you. All right. So now I want to talk about a different type of modular form, or rather actually a modular function. And it's called the J invariant. The J invariant. All right, so it's a certain modular function. Now, unlike in the other case, it has a pole when Q tends to 0. It has the explicit Q expansion. And I'll write out the first few terms. It starts out as 1 on Q plus 744 plus 1968, 84Q. Probably Ken could write a few more terms. That's all I know. So let's give these coefficients a name. I'll call this Cn. That's the usual notation, Q to the n. Okay. So unlike these other cases, this is no longer a modular form, and it behaves quite differently in many respects. So one way it behaves differently, these numbers, they are integers. In the case of modular forms, by a theorem of Deligne, you actually have a quite good control over the coefficients. I mean, they in fact grow, well, they're bounded by some polynomial. I mean, that's not even, that's easier than the result of Deligne. That's a sort of elementary fact. But in this case, these coefficients certainly grow faster than polynomials. I wrote this down. Someone else will probably tell me if this is wrong. These also maybe grow at some exponential pace, or maybe not quite exponential, but greater than polynomial pace. So these are big. That's the only point of writing these things down. So this is quite a different object than a classical modular form. Yet, on the other hand, what you find by observation is that these coefficients, Cn's, satisfy various congruence properties that look a lot like the congruence properties that sometimes occur for classical modular forms. So let me start off just by giving a theorem. This is due to Lehner. So it's a congruence. So let's say if n is bigger than 0 and n is divisible by 2 to the m, then this coefficient Cn is also divisible by a large power of 2. Explicitly, 0 modulo 2 to the 3m, well, in fact, even 3m plus 8. Okay. That's a congruence to these coefficients. Okay. So if you had a congruence for a classical modular form, you would just decompose it into eigenforms and just look at the Gauss representations and try to deduce some corresponding fact by looking at the Gauss representations. So here you can't do that. And you certainly can see, so this is maybe a trivial remark, but so G is not a sum of eigenforms. There's somehow 3 obvious reasons why it's not a sum of eigenforms. So on the one hand, the coefficients are too big. That's obviously a problem. Another thing is that this is actually a function. So in the context of modular forms, it has weight 0. And in fact, there aren't any modular forms of weight 0, basically because there would be functions on some compact space, and so therefore have to be constants. So the only eigenforms are constants, and J is certainly not a sum of constants. That's 2 good reasons, and here's a third good reason. It's hard to write it as a sum of eigenforms given that there's a 1 on Q in there. So Q inverse is a problem. Okay. So you have a situation in which you have congruences that look very much like what you might have for classical modular forms, but yet this is somehow a different object, and you want to reconcile these 2 differences. So, yes. So here's a way of just dealing with the Q inverse problem. So if we look at this congruence of later, well, it only says we're interested in the coefficient Cn where n is even. So, well, I guess I really should have said, I can still change it. Maybe here I should say m is at least 1. Otherwise, it's not even true. Well, it might still well be true. But let's give ourselves m is bigger or equal to 1. So say we're only interested in the coefficient Cn where n is even. Well, fortunately, Q inverse minus 1 is not even. So we can replace Cn q to the n by C2n q to the n. All right, so that's great. That's got rid of the Q inverse term. So you might say, well, is this an operation that you're really allowed to do with modular forms or modular functions? So if you think about this in terms of a function on the upper half plane, e to the 2 pi I tau, and you think about this as a function of tau, then in fact it's a relatively simple exercise that if ft is an q to the n, then if I let uf of t be a half, maybe this is a tau on 2 plus tau plus 1 on 2, that this is equal to a 2n q to the n. Okay, that's just writing an even function as the sum of an odd even function. You're kind of eliminating the odd terms. On the other hand, it turns out that if you apply this to a modular form or a modular function, this is still modular. So this will still be a modular function. Well, now it's actually, let's put this in brackets, not so important, of level 2. So if we do this, of course, we get what I was claiming, C of 2n q to the n. Now we can write this from 0 to infinity. So now we've solved one of our problems, the Q inverse problem. Okay. And then we still have a modular function. So we've eliminated this pole when Q is equal to 0. Of course, we haven't eliminated all the poles. Otherwise, we'd have, again, a function that would have to be constant. It's a bit hard to see where the other pole is. It's occurring at the cusp corresponding to 0. Okay. So what would we want to do with this in order to kind of proceed as we did for kind of classical modular forms? So what we would like to do is we would like to write this as a sum of eigenforms. So what we would hope is we could write this as a sum of eigenforms. That's kind of morally what we would like to do. And the problem, well, we still have these two problems. The coefficients are too big, and the only eigenforms are constant. So what we can get away with is the following. So what we might hope in order for this to be true at all is to have these phi being not classical eigenforms, but maybe some slightly more general kind of object. So in fact, we want these to turn out to be what we will call over-convergent. Convergent. Well, we have a prime 2, because we're looking at two-adic congruences, two-adic eigenforms. So that's a bit of a mouthful. So what type of thing do we want this to be? Well, just like in a case of classical modular forms, where do we get congruences from? We got congruences because these eigenforms had Galois representations. So whatever type of object we want this to be, we sort of want it to be an eigenform for the Hecke operators, and we want this to have with associated Galois representations. So this is possibly now something we could plausibly hope for. On the other hand, it's not really going to be reasonable to expect that there'll be a finite such sum. somehow we're dealing with objects that somehow are a little bit more analytic, but in terms of congruences, it's not so bad if we want to understand, say, a congruence modulo 2 to the 100th, and eventually all these guys are divisible by 2 to the 100th. So maybe we relax the hope that it's a finite sum, and now instead hope that, say, this is, say, two-adically convergent. So literally, we might, to be sort of precise about what type of objects these are, we imagine, just like in the case of modular forms, these are given by sums. Maybe I'll, instead of using an, I'll say bn, 2 to the n. Sorry. So again, these eigenforms just look like usual eigenforms, but now these bn's, well, maybe they're actually, instead of algebraic, they're now maybe in the two-adic. So I'm out of room, so bn here, maybe say, instead of just in q bar, in q2. So if we imagined a world in which we could somehow write such a formula, then we would have an explanation for these congruences for J. In fact, we might even hope for something a little bit more. Namely, we might hope that there exists hopeful, let's just say, a two-adic, thank you, Peterson in a product, and that we would actually have a formula, say u of j is equal to, well, exactly as we wrote in the other case, a sum over eigenforms, and now you just pair it with your eigenform, you normalize your eigenform, and then you multiply by the eigenform. And so you might hope that in the classical situation where you have a modular form, you can decompose it in such a way. You might hope that actually there's a much more general class of objects that includes these meromorphic functions like u of j that can be decomposed just in this way using this inner product. So let's see, I'm going to go all Ramanujan on you and say, well, just imagine what this is. We're going to call it a master formula. If we have this, then we will somehow understand congruences for the j function, at least for its even coefficients, modulo arbitrary powers of 2, in a way that will not only allow us a different way, for example, of proving the congruence of Lena, but even proving things modulo arbitrarily higher powers of 2 in terms of Gauss representations. Okay. So, unfortunately, this master formula is still a conjectural formula. On the other hand, it is known in a very special case when the level is 1, the weight is 0. These are functions, so they have weight 0, and the prime p is 2. Well, that is in fact exactly the situation we are considering, but I don't want to mislead you and say it's a question about whether it's true in general. So in fact, there's approximations to this that one can say, but it's still a very, I think, interesting question to think about, and I want to kind of lead you to this question and approach how you think about it and what the kind of objects are that are involved. All right, so this is really an introduction to what I wanted to talk about. So now, what I have to do, we start with these classical modular forms, and it's usually, if you originally think about them, you think about them in a fairly analytical kind of way. But obviously, if you want to think about them two-adically, we need to reinterpret the usual analytic approach in a more algebraic way. So probably for the rest of today's, this morning's lecture and in my afternoon lecture, I'm going to just explain some ways of thinking about these algebraically. My approach, it's certainly, what I'm going to talk about is almost completely contained in the paper of Katz, but I want to somehow explain in a way that hopefully makes it seem a little more elementary. Okay. So that's the introduction. So now let's start with the following. So we'll start with Weierstrass. I think that's going back far enough. So here's a story you probably already know, which is that how can you connect lattices to elliptic curves? So let's start with a lattice inside the complex numbers. Then associated to this lattice, you can just write down an elliptic curve. So how do you do that? Well, you write down an x, which is Weierstrass p, apparently, of some parameter z, and it also will depend on the lattice. So it's a certain sum as follows. Really, of course, you just like to take the sum over the lattice of 1 on z minus the lattice squared. But for convergence issues, you have to faff around a little bit. So that's x. I think I can still just fit y in. It's the derivative of this, and I'm sure you can take derivatives to z minus lambda cubed over lambda. Great. So you write these down, you observe they're doubly periodic, but they have poles, and then you write down some combination that is a doubly periodic function that doesn't have any poles, and so therefore it's bounded, and therefore by Liouville's theorem, it's compact. And what is that equation? Well, it's given by y squared is 4x cubed minus 60g4, just a constant that depends on lambda, minus 140g6 of lambda, where here this is just defined as the sum of 1 on lambda to the 2k over the lattice. So an explicit equation, which is exactly the equation of an elliptic curve. Moreover, if you have any elliptic curve, you can write it in this form. That's an exercise using, say, the Riemann-Roch theorem, and various other approaches as well. Okay. So the important kind of observation to observe, first of all, is that this is not a one-to-one correspondence. It's not exactly one-to-one correspondence between lattices and elliptic curves, just for the following simple reason. If you take an elliptic curve, if you take a lattice, you can scale by a constant, and what you will see is this equation will also scale by appropriate constants, which if you substitute y and x by those constants is an isomorphic elliptic curve. So, say definition, we'll say that two lattices are homothetic if there exists a non-zero scalar such that one is just a multiple of the other. And you can check that when you take, so I guess I didn't write it down, but this elliptic curve you get is explicitly given by C modulo the lattice. You can explicitly check that C modulo the lattice is just isomorphic to C modulo this different lattice. So you just map one to another just by scaling. Okay. So, in fact, the correspondence that Weierstrass proves is if you take all lattices up to the equivalence relation defined by homothety, that this is now in bijection with elliptic curves, well, again, of course, over C up to isomorphism. So one nice way to think about lattices, so of course we're allowed to scale them by anything up to homothety, so we can rotate them and scale them so that one of the basis elements are 1, and then the other basis element is some element tau. So certainly all lattices are homothetic to the lattice well, of the form z tau plus z, the sum tau in H is just the upper half plane. So it's the complex plane of positive imaginary. So, well, it's not that tau is unique, but certainly any lattice can be put in this form for some tau, and you can ask, well, what are the possible tau that it could go to? Well, another exercise that I can just fit in the bottom is that this lattice is homothetic to a lattice with a different tau in H, if and only if they're related by an element of SL2Z. I can still fit that in. So if and only if tau is A tau plus B on C tau plus D. Oop, no, I can't. But I'll put it to this page. Excellent. Well, now I can fit it in here. Excellent. In SL2. All right, hopefully some of the story is certainly familiar. All right. So now we want to think about what modular forms are. Well, instead of coming up with a definition, let's just say we think about something we might want to be a modular form. So let's think about this function here, g2k of lambda. So this is certainly a function on this lattice, but you see that if you change the lattice up to homothety, the answer will change. So you can do a computation, namely that if you scale this by a constant, well, it's just this sum on the left-hand side, you get mu to the minus 2k times g2k. So you have an equation of this kind, and this is somehow what is somehow a bit more familiar when we think about what modular forms actually are. So what would we like to do? So in some sense, what we would like to do, again, we want to translate things into a geometric picture. So let's sort of imagine we have the following. So this is somehow definition 0. And maybe okay, so we can think of first modular forms as functions on lattices such that when you scale by a constant, it comes out in some particular homogeneous way. So we'll say of weight equal to k. So I want to put some kind of, I want to adorn this definition with some remark that says it's not actually really a full definition for a bunch of reasons. We're missing some kind of conditions, so I'll just put this star here for now, which means we're going to add something to it later. So this is kind of the type of object that we want. So just to kind of translate this into a slightly more familiar form, so you can also define the function f of tau just to be the function f of the lattice tau z plus z. So you can think of then this as being f of a tau plus bz plus c tau plus d times z. If you take an appropriate, to get the parentheses correct, I have to put 1 here, and then z, and then another 1 here. All right. That probably made things more confusing, but I hope yes. It's a lattice by these two things. So now, of course, we can this is homothetic. We can scale it by this constant. Namely, we can get rid of this. We pull this constant out. We see this just should be c tau plus d to the power of I hope I get this the right way around. I think it should be to the minus, yes, exactly, to the minus k times f. And now we divide these things, we'll call this tau prime z plus z equals c tau plus b to the minus k. So here tau prime, of course, we can now think about this as f of a tau plus b on c tau plus b. So this is just a computation that maybe makes it look a little bit more like something that you're familiar with. You're familiar with these things already. Okay. So this is somehow correct, but of course if we think about modular forms, we know actually that we usually impose some other conditions, namely that these f of t are not just arbitrary functions. For example, we might want them to be continuous, or even analytic, or even holomorphic, and then we might want them to have some nice behavior as you go off to infinity. So that's what the star is, but we'll come back to that a little later. So the important thing that we want to do is elliptic curves are something that's more algebraic than lattices. If we want to generalize this to a situation in which we can talk about things mod p, well, it's a little bit tricky to take a lattice in the complex numbers and reduce it mod p. So we'd really like to talk about elliptic curves. On the other hand, unless k is equal to 0, these functions are not functions on elliptic curves, because if you change the lattice, the elliptic curve remains the same, but the function changes. So what we need to do is to fill in the following square. So here we have lattices up to homothety corresponding to elliptic curves up to isomorphism. And here we have lattices projecting down to here. And what we would like to do is just fill in the appropriate square. So in other words, we'd like to enrich the elliptic curve to get some more general object that remembers the lattice itself, not just the lattice up to homothety. So to do that, we have to think about exactly what Weierstrass gives us. So what does Weierstrass give us from a lattice? Well, what it gives you, it doesn't just give you an elliptic curve, it gives you an explicit equation for an elliptic curve. I'm going to write it out again, so it's, I'll just write it like this at this point. It gives you an explicit equation for an elliptic curve. And we know that you can change the equation and have the same elliptic curve, but we actually get the equation itself. So what we want to do is extract something from the equation that is associated to the elliptic curve that will remember the scaling in the appropriate way. So let's get the following lemma. So the space of holomorphic one forms on E, so just H0 of E lambda 1 is isomorphic to C for an elliptic curve. Okay. So one way to prove this lemma, if you were to be annoying, would be to say that's the definition of an elliptic curve. If you recall, the genus of an algebraic curve is just the dimension of its space of holomorphic one forms. But in fact, thinking about elliptic curve as C model lattice, it's also trivial, and I'll just prove it. So imagine we take elliptic curve to be E on C. So what is a differential? A differential, one form is just something that you can integrate, and you can integrate along some path, and the answer won't depend on the path up to homotopy, or even rather, even if two paths are homologous. So it's something you integrate. So we're integrating something on an elliptic curve. Well, of course, the elliptic curve is covered by the complex numbers. So certainly if you can integrate on the elliptic curve and get an answer that only depends on the path up to homology, you can just pull that back to get something that you can integrate on C, and then you have a holomorphic form on C. Well, we know what things that look like that you can integrate on C. They look like f of z dz, or even f of z to z, depending on where you are. All right, so that's what you can integrate with some f of z is some holomorphic function. And it's important, of course, that f of z is holomorphic. If you start putting in poles of f of z, then you have problems with integration. So, of course, holomorphic is there. So if we have a differential, it pulls back to something like this. But of course, because it's on the elliptic curve, it should be invariant under translation by anything of the lattice. So this should equal f of z plus lambda times d of z plus lambda. Well, d of z plus lambda, if you've ever taught calculus, you know the derivative of constant is trivial. So this is just equal to f of z plus lambda dz. And so what we deduce is that this f of z is actually invariant under translation. So again, by Liouville, it's a bounded holomorphic function, and therefore it's constant. And therefore, the differentials are one-dimensional space just given by dz. So in fact, H0E lambda 1 is just isomorphic to C dz. So the key point here is that these one forms, this is canonically a one-dimensional space, but if you think about the elliptic curve abstractly, it does not have a canonical generator. Right? If you just think of, I give you an elliptic curve, I just sort of say I'm holding it behind my back, I don't have an equation for it, and I'd say, what's the differential? There's no way to normalize it in some obvious way. So what is it that the Weierstrass equation will give us? The Weierstrass equation will give us a way of actually trivializing this isomorphism, or in other ways, finding a particular differential. So in other words, once we write down the equation, I can write down the explicit elements of this. So, well, of course, what I want to write down, I can want to write down dz. Again, well, now we'll go from elementary calculus to slightly more advanced calculus. So recall, we have our x, and then we have our y, which is dx, dz. So if I put those two together, I get dz, just by solving that equation, is dx on y. So in particular, of a Weierstrass equation, I can write down some differential. And the important thing is you can see that now, if you take a lattice and you scale by this lattice, well, this is usually a computation best done in private, but I have at least a 50% chance of getting it right since I didn't have my notes in front of me. So if you imagine what happens to the equation y squared equals 4x cubed minus ax minus b. So what happens if we scale by mu? Well, we'll get an equation y squared, I'm now using capital letters, 4x cubed. So what's happened to a? Well, a was this g4. So we knew when we scaled by lambda, this gets scaled by mu to the minus 4th times ax, and then minus mu to the minus 6. And so what we see is we can relate little y and big Y in the following way. I really hope this works out. If I can even do the computation, someone smart can help me from the audience. So let's see, we want to just substitute in for some power. It's going to be x is going to be mu squared or mu to the minus 2 times that. So I probably want to substitute in mu to the minus 2, so I get everything on this line becomes mu to the minus 6. That looks about right. Mu to the minus 2 times x. This is mu to minus 3 times y. And then what happens is that d big X on y is equal to mu times d little x on d little y. And that's correct. Great. So what that means is that when you scale the lattice by lambda, this differential that you get from the Weierstrass equation scales by the same lambda. So therefore, what we should think about when we think about modular forms, we want to think about them not as functions of elliptic curves, because we need some extra information to get the lattice. We want to think about them as pairs of elliptic curves and a differential. So let's just write that down again. So the definition of modular form has now disappeared. So remember, we're thinking modular form of weight equal to k would have the following scaling behavior. If you took f of lambda, you would get, it would behave in this way. So what we would like to think, so again, we expect lambda corresponds to the elliptic curve together with a differential omega, which just is secretly coming in terms of the Weierstrass equation from dz. And then we know that if we scale by mu, the elliptic curve will be the same elliptic curve, but this differential will now be the same mu times this differential. So what we can do is, instead of thinking about functions on lattices, which behave in a certain way, we can think about function on pairs of elliptic curves together with a differential that behaves in an appropriate way. So this leads us to now definition star 1. So now a modular form of weight k is a function f. Well, it's a function on elliptic curves together with a differential such that when you scale the differential by mu, this is equal to mu to the minus k times f of e omega. Okay. So here's kind of another way of thinking about that, which maybe I'll come back to again later on, but maybe I'll just say it now so I get to say it twice. Right, so remember this differential was just a differential for the elliptic curve. Okay. So really the right object to think about is not really the function f of e mu, f of e omega. We really want to think of f of e omega and then multiply it by omega to the power of k. Well, we don't, it's a little bit naughty to multiply differentials, so let me just kind of formally multiply them by putting a tensor in. So now we think of this object, and so now we're somehow in good shape. So now if we scale this by lambda and scale this by lambda, well, here we're just formally tensoring these together. So when you scale this by lambda, you get a lambda to the k, and when you scale this by lambda, you get lambda to the minus k. So you have an object of this kind, and this is somehow well-defined and somehow independent, really, of that omega choice. So this is somehow a way of thinking purely in terms of the elliptic curve, and this will allow us to translate it into a more algebraic picture. So let me just outline sort of where we've come so far and where we're going later on today. We're taking just a very basic analytic story, translating it into a way that can be described algebraically, and then we're going to think about elliptic curves, well, of course, points in the upper half plane modulo this action of SL2Z, and then we're going to bring in the worlds of algebraic varieties. And of course, modular forms are not functions on these varieties, because if they were functions on proper varieties, they'd have to be constant, but rather they're sections of line bundles that twist in some way, and understanding exactly how they twist will tell us exactly the appropriate line bundles and will allow us to give a definition that is well defined in characteristic P and also in more general situations. Okay. So I guess there's some food outside, and we recommence again at 10:30.